Today, I'm going to talk about the TRGB Cosmology. It's a brief introduction. I hope everybody can understand the essence of this TRGB Cosmology. I've been leading a project, the team on TIPSNO in Korea, and also I have been a member of Carnegie Chicago Hubble team, CCHP. So I know both. Sorry. H0 representing the today's expansion rate of the universe. As everybody knows, I claim and you agree that the most debated parameter in cosmology nowadays. Then how to get it is the TRGB. That's what the TRGB cosmology does. So today I'm going to give a brief introduction in the beginning and then tell you about what the TRGB is and how to derive a TRGB distance to a galaxy. And then going to show two examples. One is on supernova cosmology, and the other one is a dark matter and H0. And finally, I'm going to give a summary. Introduction, cosmograph, which is on the study of structure and the kinematics of the universe. For this, we need both parameters. One is distance for looking at structure, and the other one is velocity for kinematics. In observation, it's very easy to get a velocity of a galaxy from the measurement of redshift. So in general, the error for the velocity measurement is very small, almost negligible in cosmology in many cases. On the other hand, galaxy distance is a different matter. I like to argue that galaxy distance is the most fundamental parameter to cosmology. Because without distance, you cannot do anything in modern cosmology. However, in practice, galaxy distances are very difficult to estimate. It's possible, but often the errors are large. So in general, the errors of distances are much larger than errors of velocity measurement. Cosmological kinematics is described by a motion of a galaxy, but the motion or the velocity of a galaxy measure is actually composed of two components. One is due to the Hubble flow, and the other one is peculiar motion. The Hubble flow is a function of curvature of the universe and omega lambda and omega matter, etc. And peculiar motion is mainly due to the local gravity of some object which is dominated by a dark matter. So a peculiar motion actually is comparable with local dark matter and also Hubble flow. So it's very simple to get cosmological kinematics if we have a velocity, but we need also distances. So we can make two cases of H0 cosmology. One is to study Hubble flow. For this purpose, we need to use sources with Hubble flow velocity much larger than peculiar motions. For this example, distant galaxies in the field. And second one is to study not only the Hubble constant, but also a dark matter distribution. For this purpose, you can use sources with peculiar velocities larger or comparable to Hubble flow. For example, nearby galaxies around clusters, they are very useful targets for this goal. So accurate distances are needed for both of these goals, which can be done by TRGB cosmology. This is an old history of H0 in 20th century, since Lemaitre 1927, and also Hubble 1929. There is a large variation of Hubble constant during the last 7 or 8 decades or so. Even today, the scatter of the Hubble constant measurement is very large, but in this century, we have different views of its determination. So basically, you are using two ways to estimate the value of the Hubble constant. One is the derived H0 directly from the local universe. So basic tool has been a cosmic distance ladder. And one of the most popular candles is a Taiwanese supernovae and many other things. And another method for this one is direct methods based on modeling. For example, gravitational lenses or water or megamasers or gravitational wave sirens, etc. And second way is not look at the local galaxies, but look at very distant sources. For example, cosmic microwave background radiation, etc. So we get the value of our parameter at higher shift and extrapolate it through the today to get the local Hubble constant, which is called inverse distance ladder. Basically, based on modeling of the universe. So the typical example is MBR and also baryonic oscillations, etc. But as of today, we know the Hubble tension is being discussed. In summary, the value based on the Cepheid calibrated supernovae 1A is 74 plus minus 1.4. And the team who is leading in this project is a Hughes team led by Adam Rees. They have been presenting their values from 2016 to today. So they're presenting a value of a constant with an error of 2%. On the other hand, Planck 28, a value based on CMBR, which is about 7 kilometer per second or megaparsec smaller than a Cepheid calibrated supernova 1A value. And their error is less than 1%. So the difference between these two measurements is 6.9 kilometer per second per megaparsec, corresponds to about 10%. So this difference is at the level of 4 to 5 sigma. So if the difference is 4 to 5 sigma, then it's serious. So now we call it Hubble tension. And everybody is wondering how to resolve this one. That's the question. However, there is a caveat given by Michael Turner long ago, 1998. He made 2 comments in this slide. One is you're an astronomer, so you don't understand statistics. At that time, probably yes, but not anymore these days. Because every astronomer has to understand the statistics, otherwise you cannot do any good job. And second comment is never believe any theory that fits all the data, because some of the observations are always wrong. I think it's still true. So we have to be careful when we are dealing with any value based on modeling or theory. Anyway, so Taiwanese supernova cosmology or supernova cosmology, yeah. So Taiwanese supernovae are a very powerful standard candle for studying Hubble flow. The first step in supernova cosmology is calibration of the Taiwanese supernova luminosity using precise distance indicators like TRGB or Cepheid. So this is a modern ladder for supernova cosmology. In the past, we have been depending on old ladder given in the right panel here. This is given in the Wikipedia, but this is very old and obsolete ladder. And modern ladder is given here. So TRGB was surface are directly calibrated using geometric distance anchors, and then using TRGB and surface to calibrate the luminosity of Taiwan supernovae, and then using a sample of large number of supernovae at large range of distances, then you can get H0. If we cover a much large range of redshift, then you can determine not only Hubble constant, but also Q0. So, what is a TRGB? In the old textbook, there is no mention of the TRGB because it started much late in 1993. TRGB observations. This is a map of a famous globular cluster in our Milky Way galaxy, basically M55. If you get the CM diagram of stars in this globular cluster, you'll get a plot in the right here. This old photometric system, B band and B minus V color. So stars are found along this main sequence and then getting colder or yellow and redder or brighter, and this part is called a red gem branch. And then the brightest part of the red gem branch is given here, where helium flash starts. And then stars move to very high temperature here. So they evolve along horizontal branch and along AGB. So this part corresponding to the helium flash of low mass stars. But seen as the brightest point of the RGB in the column diagram, that's a TRGB.
Can we go back to the slide then? So it's called the horizontal branch, but it doesn't look very horizontal in your plot.
Oh, this one is not at all horizontal. Actually, horizontal part is this one.
Oh, yeah, okay.
Yeah, there is a variation of curvature here. So, but traditionally, the entire part is called as horizontal branch.
Okay,
Blue horizontal branch and red horizontal branch. So blue horizontal branch shows actually like a vertical feature sometimes. Just traditional, conventional naming.
Okay, thanks.
In astronomy. And also, if you take a look at the evolutionary track of low mass stars, they follow this temperature and luminosity. So stars evolve from the main sequence, this is point solar mass. So they follow RGB and reaching a helium flash stage, and then a horizontal branch. Also, if you take a look at a slight different range of masses, in the left, the blue ones are low metallicity and the red ones are high metallicity, but the three different tracks are for the mass of 1.3 solar mass and the 1 solar mass and 0.8 solar mass. So the brightest part of the RGB, they are showing almost similar luminosities. So in terms of stellar evolution theory, we know how TRGB is produced and what average stage they correspond to. So you understand both the TRGB in observations as well as in theory. Then, what are the pros and cons of TRGB? They were described clearly in the old paper, 1993. Here, Lee, Friedman, and Modor. It was the first quantitative analysis of the TRGB method, showing the power of the TRGB. Before this era, actually nobody knew about the TRGB, how reliable it is. But after this, now everybody knows the power of the TRGB. The strength, first of all, it's not variable stars. So you need only one single observations. If it's variable, then you need multiple observations. And TRGB is almost free of extinction because RGB stars are mainly located on the halo where interstellar dust is almost nothing. And also, it is almost independent of metallicity at I band. I band corresponds to about 800 nanometer. And TRGB is seen any types of galaxies, from spiral galaxies, irregular galaxies, to elliptical galaxies, or whatever galaxies. Because now I know, and you all know, that all galaxies include all the stars, although they have some young stars as well. So this one is ideal for HST and also for coming James Webb Space Telescope. And the weakness of TRGB, first of all, the density of the RGB stars in the halo is very high. So we need a high spectral resolution. So it's been difficult to measure the TRGB in the ground-based observations. But with HST, we can do a lot of things. So high spectral resolution is not a matter. And also RGB contamination. The brightest part of the RGB is composed of not only old RGB, but also a little bit more evolved stars, which is called AGB, asymptotic giant stars. But the fraction of AGB is much smaller than the density of RGB stars, so we can distinguish between AGB and RGB. But sometimes it's difficult. And the third one, the blending in the crowded field. When the stellar density is too high in a field, then some stars get blended so that you can measure the magnitude of a star actually brighter than real magnitude. But this also not significant. And the range of TRGB application is distance closer than, roughly speaking, 35 megaparsec with HST. On the other hand, surface, which everybody knows. Well, let me start with this first, the weakness. First, surface, we need multiple observations because the periods of surface range from few days to more than 100 days. So you need to observe the surface for long period with multiple and they suffer from high extinction because they are located often in the suffering region where interstellar extinction is high. And also, the luminosity of surface has been known to depend on metallicity. And the relationship between luminosity and metallicity has been controversial. It's not clearly known. And also, surface are found only in late-type galaxies, young galaxies again. So, spiral galaxies or irregular galaxies. You cannot find any classical surface in elliptical galaxies. Strength of surface, we can surface easily if we get light curves of the stars. And surface is often brighter than TRGB at V and I band. But if you go to the near infrared band, then TRGB gets brighter than surface. And the range of application of surface is around 40 megaparsec with HST. So I'd like to show some examples of TRGB. The first example is NGC-185, which is a dwarf elliptical galaxies close to Andromeda Galaxy. This is the CMD of the stars in one of the halo fields around NGC-185, given by In-Sung Jang, who's an expert on the TRGB. So this star shows a bunch of stars here in sequence and RGB stars. Horizontal branch stars, here again, they are not horizontal but slanted, but anyway, they are horizontal branch and RGB stars, and TRGB is here, clearly seen. Well, it's interesting to compare this very nice, fancy, modern CM diagram of this galaxy the old one I presented in 1993. Back in 1993, CFHD images were the best at the time from the ground-based observations, because this HST was not available at the time because of some problems. So this is the best CMD at the time, but the old CM diagram covered only this part. So as of today, it's amazing to see how deep you can go with modern HST photometry. Second example is a Leo A. It's start forming irregular galaxies. This HST image, you can see many yellowish dots, which are RGB stars. Some bluish stars, they are young stars. So this galaxy shows complex stellar populations from young to old. But if you take a look at the CM diagram of this galaxy in the right panel here, so young stars, young main sequences follow, and old RGB stars here. So again, the brightest part of the RGB is clearly seen, indicated by the red arrow. So even in this kind of galaxy, which shows young to old stars, so clearly they show TRGB. And the upper part is a mother CMD showing in the stars with a large range of ages. So the blue one is about only 10 million years, and the red one is 10 gigayears. So the CM diagram of the theoretical stars looks similar to the following observational CMD. We know what stars they are, not only observations, but also from theory. Another example is NC 4395. It's a low surface brightness spiral galaxy with forming stars. Again, here lots of stars in the main body and the outer field, and the bluish ones are young stars. So the right part, the CM diagrams of different combinations of filters, KNI and UV to U, etc. But here, the I versus V minus I, again, this one is main sequence stars, very young stars. And here, bright red stars, which are red supergiant stars. They are also very young. Ages are typically 10 to 20 million years. And then going to redder and fainter, you can see two discontinuity. One is upper part corresponds to the tip of the AGB, so it is called AGB, and lower part, another discontinuity, which corresponds to the tip of the RGB, so TRGB. So sometimes you can be confused by TAGB and TRGB, but the number density of RGB stars is much larger than AGB, so you can tell what they are. Then, how to derive a TRGB distance of a galaxy? Well, the principle is simple. Detecting a jump in the luminosity functions of RGB star candidates. Here, I mean by the luminosity functions is a number distribution of stars as a function of magnitudes. Often, three methods have been used. First one is direct edge detection method, which I started using long ago, and even today, this is still popular. But there is also improved method, which is called close edge detection. And at the same time, different lines of method has been used based on maximum likelihood method, which I'm going to introduce each of these. Okay, so this example for TRGB detection. First of all, let me show this image, this color image. Sorry. Yes. This color image of this galaxy. This galaxy is not at all exciting or fantastic. It's one of the typical small, faint dwarf galaxy located at the distance of about 10 megapascal or so. And we used HST images covered by a white rectangle. The middle panel shows the F184W, which is corresponding to about 800 nanometer wavelength image. So in the HST image of this field, you can see a lot of stars. And the right panel shows the columnar diagram of the stars we found in the HST image in the outer part. So again, blue stars are MH1 stars and the young supergiant stars, and a small number of vertical structure objects, which they are red supergiants, and then RGB. So the brightest part of the RGB is seen here. Here the magnitude is around 25.647, so it's very faint considering the photometry. And if you plot the stars located within the shaded area, the gray shaded area, they are represented by red circles in the middle panel. So the red dots are locations of candidate RGB stars. So they are located in the halo part, although this galaxy shows both young disk stars and also halo stars. They are mixed together in the field, but we can segregate RGB stars using TM diagram. So selecting the RGB candidate stars in the shaded region, and then you can make a luminosity function of these stars. This one. So this upper part's luminosity function of the RGB stars, so the number is very low in the prime magnitude, and it starts increasing up till here. So how to detect the TRGB in this diagram? We, in general, involve luminosity functions with a Sobel filter, which is given here. The role of Sobel filter is to enhance the signal of jumping in the distribution. So if you convolve luminosity function to Sobel filter, then we get a value or distribution of edge response, which is given in the low panel as a function of magnitudes. So this edge response is low here, then it shows a maximum around this area. The value is given here, 25.75 plus or minus 0.09. You can estimate the error of this using bootstrapping. So this is based on the direct edge detection. And this has been a very classical technique since I used from 1993. But recently, a better method, which is called Galois direct edge. I should have removed the direct Galois edge detection. In this case, we smooth fine luminosity function of bin size only 0.01 magnitude with the Galois. What is Galois? Gaussian node, locally weighted scattered plot smoothing. So it's kind of a smoothing algorithm. So this very fluctuating gray lines shows the fine luminosity function, and the side little line is Galois smoothed luminosity function. If you apply a Sobel filter, here in this case, -10 plus 1, then you can get edge response with the red lines here. So from this, you can get the value of TRGB magnitude, 25.74 plus or minus 0.03. So this one is very close to the direct edge detection method value, but the errors are much smaller. And the third method is Mesmerized method. This is based on modeling. So if we use a model of luminosity function described by this function. So the function of this luminosity function is given by solid lines here. And the histograms are luminosity functions from observations. So if we fit this function with the observational luminous function, then you can determine the slope of the bright part, it's called AGB part, and slope of the fainter part, it's RGB slope, and discontinuity between AGB and RGB, which is described by a parameter B. From this, we can estimate the TRGB magnitude, 25.74 approximately 0.02. So if you compare all these three, it's amazing. They show an excellent agreement. The difference is only 0.1, and measurement errors are typically 0.02 or 0.03. So measuring error over 0.02 magnitude corresponds to 1% in distance. So you can get the measurement of TRGB magnitude leading to a 1% error in distance. This is amazing, because in the past, if you get 10% error in distance estimations, every astronomer was very happy. But not anymore these days, because of the Hubble tension. Then, so once you get apparent magnitude of TRGB, then we need to calibrate the TRGB magnitudes. So in the old days, we calibrate the TRGB magnitude using photometry of Milky Way globular clusters given by Parkinson and Armand. So I made some adjustments. So adapting I-band absolute magnitude of the TRGB plus minus 4.0 plus minus 0.1 magnitude. This was a very conservative estimate time. And so the right panel shows the calibration of the TRGB, showing the Milky Way region branch based on 4 globular clusters with a large range of metallicity, and the lower part corresponding to similar RGBs from theoretical evolutionary tracks from Yale 1987 models. But later, around 24 years later, we presented a new calibration of TRGB. Here, we used around 8 galaxies of different types with the different star formation history using HST images. We combined all those galaxies into a single system like this. So this is the locus of TRGB for a wide range of colors. So this is a blue part, is almost constant, is almost parallel. So almost parallel, but as you go to a red color, they get steeper. For this measurement in general, you are using only the blue part. For this, we had to use geometric distance anchors. One is NG4058, which is based on H2O mega mason. And another distance anchor is the LMG. The distance is based on detected detection binaries. So if you adopt the LMG anchor, we get absolute magnitude of TRGB minus 3.97. And if you adopt the NG4028, then this magnitude will be minus 4.03 or so. And 2 years later, CCH15 provided another TRGB calibration based on multiband VIJHK photometry of the LMC. But here, they adopted a slightly higher extinction for the LMC. The extinction value at the I band is a 0.116 plus minus 0.07. In the past, often 0.1 has been adopted. But the value of the extinction for the LMG is still controversial. Even last couple of months, they present different ranges of extinction measurement for the LMG, ranging from 0.07 to 0.22. So it's still an open problem. But anyway, here the absolute magnitude of the TRGB at the I band is minus 4.05, plus minus 0.04. This error is much smaller than in the past. So this is a comparison of several TRGB calibrations and observations on theory. So the black line is our old calibration, minus 4.0. And the red one is our new product calibration. Very similar to, there's a little change between the Lee 1993 and Dang and Lee 2017. And Friedman et al. 2000 is slightly higher. But within the error, they are consistent. On the other hand, rich error calibration is given here, and based on the theoretical models is given the science, etc. But anyway, they are very similar up here. And if you go to a longer wavelength, like a near infrared from the optical band for VNI, then they look like this. Optical CMD is I versus V minus I, and the right CMD shows like a K versus 900 nanometer to 2 micron. So TRGB magnitude is around minus 4 in the optical I band, but about 2 magnitudes brighter at 2 micron band. So if we use the James Webb Space Telescope, which will be launched next year, then you can reach magnitude to fainter, so we can go further. Okay, so now you understand, I guess, what the TRGB is and how to apply TRGB to get a distance of a galaxy from a photometer stars of a fine galaxy. Application number 1 is supernova cosmology. So the TRGB is a powerful tool for supernova cosmology to determine the Hubble constant. Popular types of supernovae are type 1a. But there is also another type, which is called type 2. The progenitor of type 2 are massive stars. In theory, there are more type 2 than type 1a. But type 2 are found only in late type galaxies because they are massive stars, young stars. And the light curves of type 2 supernovae show a large range of luminosity. So the errors of stellarity, so they're not as powerful as type 1a at this moment, but some astronomers are working very hard to utilize type 2 as well. For example, Diego et al. Recently presented a value of Hubble constant they get using type 2 supernovae. The value is similar to the known ones, but with large errors. But anyway, so I have been doing a project, it's called Deep Snow, with my students, In Sung Jang and also other students from 2012. The Deep Snow means the TRGB for supernova galaxies in the universe or at SNU. So this is the example of the TRGB galaxies. NGC 1309, which hosts Supernova 2012K. And to date, this is the champion in the TRGB measurements. This galaxy is located at around 33 megaparsecs or so. This beautiful galaxy, this spiral galaxy. So in the past, we have just enjoyed the beauty of this galaxy from the images. But today, we can do a cosmology with this kind of galaxy. How to derive H0 from supernovae is very simple. From the relation between the apparent distance modulus. Distance modulus is just a difference between apparent magnitude and absolute magnitude. And this is a function of redshift for given H0 and Q0 the relations are given in the below. So if you look at the relation between m minus m distance modulus, or if you know m, then relation between the paramagnetic as a function of redshift, then you can estimate the value of the parameters h0. If you go to a very large range of z, then you can also estimate the value of the q0. So the supernova cosmology is basically using two parameters: apparent magnitude for low Z supernovae and absolute magnitude of supernovae from TRGB or cell phase. Another formulation also is given this. Basically, same thing. Here, the Hubble constant is given as a function of absolute magnitude of supernovae and also intercept of the Hubble diagram. Hubble diagram is the relation between magnitude versus distance or redshift. But one thing we need to know is the errors for candle cosmography. We like to know D and V. However, we cannot measure distance. What it can measure directly is only magnitude of a candle. So the errors in magnitude leads to errors in distance and h0. Astronomers use distance moduli, which is defined m minus m, here or mu, 5 times the logarithmic value of distance minus 5. From this, you can derive the relation between this fractional error of distance, fractional error of h0, and fractional error of magnitude. So if you have an error of point of magnitude for supernovae or candles, then corresponding error of the h0 will be around 5%. So you have to keep in mind. So we presented the result of Gibbs law 2017. Here we show the comparison of h0 based on Cepheid calibrated supernovae, which are blue symbols. And here yellow ones by Friedman et al. At the time, CHP teams, and blue ones are Schuss teams led by Reis. And on the other hand, the black circles show the CMBR, the beginning part based on WMAP, and the purple ones are Planck ones. So the value of the CMBR h0 kept increasing in the past decades. So current values here. And Cepheid calibrated supernovae stays almost constant or slightly decreased. And 2012, we presented a value of 65 here with one supernovae. Then we increased the number of supernovae galaxies using TRGB. So 2013, 2015, and the final sample based on 6 supernovae host galaxies is here. So this value is located between Cepheid and Planck. And the errors are larger than the others. So this measurement is consistent with the Schuss values and also Planck values. But we need to decrease the error of this one So later, CHP and us started collaboration. So if I'm going to show the results, I'd like to mention the difference between tension problem crisis. Difference level is 2 sigma, then we call it the curiosity, 3 sigma, maybe tension, and 4 sigma, discrepancy of problem, 5 sigma is crisis.
So I think David Gross is responsible for the word crisis here.
Who?
David Gross.
Yes, okay, I should put a reference.
Well-known string theorist, right, sort of.
Okay, that's good to know. So it's not from TRGB calibrated supernova 1A was presenting 2 years later from the CCHP team. It is based on larger sample of supernovae host galaxies. It's 18, so it's much larger. So this is a Hubble diagram of supernova 1A. The red ones are calibrators, and the blue ones are more distant supernovae. And the line is a fit using the model, so that it is excellent, pretty good estimate. So this is a summary of the H0, 1 till 20 in 19. So blue ones are safe phase, and gray ones are CMB, and red ones are TRGB. So TRGB has been between safe phase and CMB in the past several years, but the errors kept decreasing, and we are still trying to decrease the error bar. So this year, CCHP team presented another estimate based on improved value of the LMC extinction. So the value is this one, 70 plus minus plus 1.3 or so. And Planck value is this one. So this Planck value and safe phase calibrate supernova 1A, and the red ones is a TRGB calibrate Taiwanese supernovae. So it's between safe phase and Planck. So TRGB calibrate supernovae 1A value is consistent with both Planck and safe phase. But the Planck and safe phase calibrate supernova 1A, they are different at 4 to 6 sigma. So the future of Taiwanese cosmology, there are 3 directions. One is going to further within the infrared with the James Webb Space Telescope, which will be launched next year. And also we need to increase the number of supernova kilometer galaxies. At this moment it's 18, but we need to increase that number. And also we can reduce TRGB as well as safe phase errors with the Gaia. So Gaia people are working very hard. But at this moment, the errors are still too large, but soon we'll get a much better estimate of the Gaia data. Then application number 2, which is
지금은 부재 중이므로 전화를 받을 수 없습니다.
sorry about the phone message. This is it's on dark matter and it's not. Actually, it's on the Vogue info. Totally different from supernova 1A cosmology. Galaxies around the Vogue cluster are affected by the gravity of Vogue, showing infrared motion toward the Vogue. So their motion in the universe, the lambda, can be described by these terms. So gravity and the Hubble flow. Then Vogue-centric velocity of galaxies in Vogue is given as a function of Vogue-centric distance, given H0 and mass of the Vogue, or size of the cluster. These equations, this kind of numerical solution of the models. Here, our lot is a zero velocity radius where the cluster is separated from the field in the Hubble flow. The velocity of galaxies at R lot is 0. So if you have a velocity and distance of the infrared galaxies, then you can determine both H0 and the mass or size of dark matter in Vogue cluster. So for this modeling, to derive the value of the parameters, we need accurate distances, that is TRGB distances. So we need a very accurate distances of these galaxies. In the past, it was possible in principle, but could not avoid large errors. So for this, we are using galaxies toward Virgo, which are located between the local group and the Virgo. And the distribution of the galaxies are given here. So this is the center of the Virgo cluster, where M7 is located. And this is about visual radius. And this bunch of galaxies here. And the color of the circles shows the relative velocity. So the dark blues corresponding to Virgo velocity, and they have these galaxies have much smaller velocities. So this shows they are unfolding to the Virgo center. So they are unfolding galaxies. We are adopting the distance and velocity for like this. By the way, this work is mainly done by Myung Gyoon, my graduate students, who is going to give a result this year. What is the result? So this is a relation between Virgo velocity, Virgo-centric velocity, and Virgo-centric distance. So galaxies are located here, and the horizontal line is zero velocity, and the radius around 7 megaparsec represents zero velocity radius. So this part is inside of the Virgo cluster, and outside this, they are following mainly a Hubble flow, as well, although they are affected a little bit by the impulse motions. So if you feed the models to this data, or you derive a red dashed line. So the model fits very well the data. So from this fitting, we derive the values of H0, as well as R0 and M, and also other parameters. So in this diagram, we plot the value of the Hubble constant measured from Virgo in 4 to the large red circles. And this red boxes is a TRGB calibrated supernova 1A from CCHP, and this diamond is TRGB calibrated Taiwanese supernova 1A from TIP Snow from Zhang and Lee. So so Taiwanese supernova A TRGB and Virgo in 4 TRGB, they are totally different. They are totally independent, but they show similar values of the Hubble constants. So the measurement based on the TRGB, either on supernova 1A or Virgo in 4, they do not show any tension with Planck values, although surface show tensions. Of course, our measurements are still between Planck and surface, and Virgo in 4 measurement is still a little bit larger error than the others. But considering all these, they are pretty good. Other tracers, I wouldn't mention other tracers, but in another talk on kias, I may mention those later. So
can I ask,
in summary,
can you reduce your error on the infall? Like, what would you need to do? You'd need to find another system with infall?
reducing, we need more galaxies, but we are using as many as possible galaxies at this moment. So it's not easy to increase the number of samples. It's kind of intrinsic limit. But this is the best estimate to date. So in summary, the TRGB is a precise distance indicator based on geometric anchors, being an excellent tool for H0. The value of H0 is still evolving. So as of today, the Hubble tension is, I think, between 2 and 4 sigmas. the future of H0 tension, we need to work further. So stay tuned. So I'll stop my lecture here. Please, any questions or comments?
Well, I guess any questions or comments?
I have a question.
Sure.
Hi, my name is Maurice from Putten. I'm joining the seminar through Zoom. I have one question that goes back to the basic ansatz in using the red giant branch for this purpose. And that is the notion that the stated assumption is that for each galaxy, the maximum light in this red giant branch is the same. But as you know, the red giant branch consists, of course, of a population of stars. And if that population has a redshift dependence, for instance, it might be somewhat larger, slightly with some minor dependence at larger redshift, then of course the maximum will go up, because if you take the maximum of a subsample of a given distribution, then that maximum will depend on the size of that subsample. And so I didn't find any discussion on this matter in any of the papers from your group. And so I'm wondering if you made any observational constraint on this dependency.
Well, so you are asking any dependence of TRGB luminosity on the redshift?
Yeah, well, yes, indirectly, because the size of the population may depend on the redshift.
Right. But first of all, the luminosity of the TRGB changes little for stars older than 3 gigayears. So in the low redshift, they change little. So they have no dependence on the redshift. One thing. And second thing is the supernova host galaxies, which are used for the calibration of TRGB, they have a redshift of almost 0. So there is no problem at all on the redshift dependence of TRGB magnitudes. So as long as the stars are older than 3 gigayears or so, their luminosity is almost the same.
You mean it does not depend on the size, on the number?
Others.
You mean it does not depend then on the population number of RGBs in a given galaxy, whether it's 100 or 1,000, the maximum will be the same, is what you're saying.
That's right, because you are looking at the luminosity of individual stars, and then using the distribution of the stars to measure where the change in the luminosity happens. So it's not based on the combination of stars. It's based on individual stars. So
I thought you were taking the maximum of the population.
Yes, maximum, but here, the maximum of the RGB.
Yes.
Yes.
But that maximum in principle depends on the number of RGBs in your subsample.
No, not at all. The maximum is determined by the individual stars, not by the combination of stars. So there may be some misunderstanding or confusion.
No, I think there is some misunderstanding, because in the press releases and the popular accounts, and then also from my own angle to look at this, the analogy was made, if you take a class size of people, then there is a maximum size of a person in the class. That's fine, but that maximum will depend on the size of the class. So what you're saying essentially is that that analogy is then not a correct analogy that people have made in the more popular descriptions.
Sorry, Royce, where did you find this popular description?
Oh, it's actually in a press release by one of the 2019 Friedman paper.
Okay.
And so it was tried to convey to the more general public the basic principle. And anyway, I just noticed this a few days ago. My question actually is from much earlier. So ab initio, there is, of course, a dependency on the class size, that is to say, on the subsample size. Unless, of course, you have good reasons to say that it does not depend on the class size. But if you, for any distribution, if you take a subsample, then the maximum of that subsample depends on the size of that subsample. So if you want to say this is not relevant, you have to quantitatively demonstrate this. And I didn't find this discussed, and it's even more contradictory, as I said, because it's in the press releases. I didn't find this discussed at all in the papers.
So this is more or less a comment for the CCHP collaboration.
Well, it's a serious issue because we are looking here at, percentage issues, whether the estimate given will move up or down by 1% by this effect. And, to simply say it is not relevant, I think is too much of a shortcut, because we are not talking about large effect. We're probably talking about very small effects that then in the final error budget may become very important, moving things from 2 to 3 or 3 to 4 sigma. So I'm not satisfied right now, unless it is explicitly demonstrated that you can ignore this.
Okay, thanks, Maurice. Actually, can I ask a related question, which is,
sure.
So basically, it seems like your central values of the TIPS new results have sort of bounced around from 65 to maybe slightly higher, 71 to 70. Are they all consistent with each other?
Between which one and which?
All within 2 sigma, are they?
Yeah, they agree within 2 sigma.
They're all within 2 sigma.
Right.
So it looks like we still have a long way to go on TRGB. Or maybe things are progressing very quickly, are they?
Progressing quickly.
So which results do we have confidence in? I mean, it does seem like H0 could continue to evolve.
I didn't get your point.
I guess I'm saying that as you started off with some small sample of supernovae, then you've added more supernovae. Now we're at the stage where I guess we have 99 supernovae with CCHP.
Right.
And then the result has gone from 65 to 71 to essentially 69 point something. Do you think this is going to be more or less your final answer?
Yeah, but we can now go to 99. At this moment, 18. And we need HST or JWST. So increasing the sample, even by a small number, but it takes time. But once you get, for example, 99, sure, yes, because the errors will be smaller than, the factor of some.
Hello, this is Shaheen. May I ask 2 questions?
Sure.
One is, what do you think that is sort of wrong with the Cepheid calibration, that they are giving a much higher value for
What's wrong
H0?
with the Cepheid in Cepheid? Add-on, he may tell you or may not. But there is one interesting paper by F. Palacio this month or last month. He analyzed again the data of Hughes and CCHP. And then from that analysis, he suggests one possible solution to resolve the tension between the Cepheid calibrated supernova VNA and Planck. So his conclusion was a bias of 0.1 to 0.15 magnitude in the Hughes galaxies may remove the tension. That's one possibility. But I don't know whether Adam will accept it or not.
And the second question is, depending on how we measure H0, I mean, at which redshift, we may see a sliding effect. So basically, if we use more local data, we may get a higher value for H0. If we go to a bit higher redshift, we may get a lower value. And This feature has been reported in the Holy Cow experiment, and we have also seen similar feature from low redshift data in cosmological settings. Could it be related to the differences at 2 sigma level that you're reporting?
Yeah, that argument has been around to explain as a possible solution the tension between Planck and Cepheid heavenly supernovae. But I like to emphasize here the TRGB from Vogo info is right at the local universe, but do not show any large value of Hubble constant, which is not consistent with that argument.
Okay. Thank you.
Any more questions or comments? Any questions from Cassie? Participants? No? Yonsei? No? If not, then I guess we thank our speaker again. Okay, thank you very much for a very interesting talk. It's really,
Okay, thank you for listening. Okay, bye-bye.
Bye-bye.
수고하셨습니다. 이 교수님.
고맙습니다.
예.
고맙습니다.
Okay, I just found the link to this classroom example. And it's from the Carnegie Science discussion.
Hey, Maurice, you probably need to send it on, right?
Sorry?
Send it on by email.
Okay.
Yeah. To us, right? Yeah.
Okay, I'll repeat this in an email.
Okay, or we can, I don't know if you're going through this thing on Friday. Maybe I see you on Friday.
Yeah, but I would have liked to have heard Myung Gyoon's response to this.
Okay, then. Okay, send it on by email.
Yeah.
Okay, thanks, Maurice.
Okay.
Okay, so may I leave?
Yes, you're all done. Unless you want to talk to Maurice.
I mean, well, yeah, somewhat belatedly, but I just put in the chat box the link to the example I was referring to, although my question came from a different angle, but it's the same issue. And so maybe you can give some thoughts to this. I mean, you don't have to reply immediately, but this refers to the, the tallest person in the room without any discussion on the dependency on the size of the classroom.
Okay, so this is on the sample size of TRGB stars. That's what you mean?
No. Well, I invite you to look at the link because it more specifically makes reference to your work and has a little clip that demonstrates this, or supposedly illustrates this method.
Okay, well, I just like to mention that we need a sample size of more than 100 stars for measuring TRGB. But if the number of stars is smaller than 100, then you may have a different
no, that's
estimate.
fine. That is fine.
Yeah.
But your sample size, how do you control? My point is that the total number of red giant red giant stars in that class in a galaxy is something you cannot control, right?
But on a planet, because the most number of the most popular stars in a galaxy is RGB stars.
Yes, but that number varies from galaxy to galaxy. That's my point.
But as long as you sample, 100 TRGB stars or so, then that's enough. You don't sample all those stars.
No, that's
So
right. But the underlying, that's right. But the underlying, okay, maybe my argument is slightly different. You have, of course, the total number of red giant branch stars in the universe. That's a huge number. And each galaxy basically takes a subsample out of that underlying ground PDF. Now, each galaxy, therefore, has a slightly different subsample of that class of stars. And the size you don't know. It's very large in each galaxy, but it will vary from galaxy to galaxy. Then on top of that, you are selecting 100 of the brightest, obviously, of that subsample. And essentially then you're selecting a peak of that subsample, but the size of that subsample may vary and you don't know the size of that subsample that is present in each galaxy. That's my point.
But that's no problem.
Fine, then you please convince me that that is no problem, because it needs some explanation, I think, to argue quantitatively that one need not worry about that. You cannot take that at face value. At face value, it's an issue.
Sorry. Okay, so I think this may be where to...
Okay. Anyway, I have to stop here. Okay.
Yeah, so I gave you some links. And
okay.
In my lectures on modern astronomy that I developed for last term, I went into much more greater detail on this. So I'm happy to make it very quantitative, this issue. Okay, and the reason it triggered my interest is because I'm dealing a lot with this issue at a technical level in my GRB business and my gravitational wave analysis issue, where you encounter the same issue, encountering a max from a subsample of a certain PDF. So technically, I'm familiar with the issue.
Okay.
Okay. Thanks for the comment, Maurice. We'll discuss it on Friday, right? Or we can do it on.
Of course we will. But again, I would like to get the speaker's comment on this issue.
Okay.
Okay.
Okay. Well, thank you very much for the lecture.
Okay. Bye bye. Thank you.
Okay. Bye bye. Thanks a lot. Yeah.